Welcome back. This would be, I think, the fourth video of Module 7. We're talking about the raster model, moving our way into raster analysis. Last time I gave you a few examples of available data sets out on the internet. There are elevation data sets, there are climate data sets, there are land cover data sets, and there are imagery data sets you can get. So this time we're going to start talking about analysis and some of the processing you can do with your raster data. You need to keep in mind that you can convert between raster and vector data. So if you have some data that are vector and some data that are raster, you need to do an analysis. You can actually convert one form to the other and do the analysis based on a common data model. So this example shows you, of course, real world represented in the vector model as points, lines, and polygons, and in the raster model as a grid of cells, each cell having an individual uniform value across its area. Can convert back and forth. So how would you go from raster to vector? Well, if you start with vector and go back to raster, you can start with points, you can start with lines, or you can start with polygons. If you convert points to rasters, what you will get are cells that the points fall inside having a value, and all the other cells where there are no points in the vector being no data cells. So that's pretty straightforward. You have a grid where most of the data in this case is no data, and the rest is the value of the points that are being transmitted across. Lines, it takes the value that's associated with a line, an attribute or an ID value associated with a line, and it assigns that value to all the cells that the line runs through. And so you can see this is kind of one of the issues when you go from vector to raster. Linear features become stair-stepped, and you see pixelation in here. So because there are distinct boundaries in this vector representation, it's difficult to represent that in raster unless you make the cells really, really small, and then you can make it appear to be a line, but when you zoom in it'll still be stair-stepped. Polygons, similarly, when they're converted to raster, you get the same stair-step representation, and there's some value associated with that polygon. It could be an attribute or an ID value that will get assigned to all the cells that fall underneath that polygon. Here's an example. This is the gap analysis data set for Utah. So this is the land cover data set for Utah. It's a raster data set, and remember there are like 500 and some different land cover types in the most detailed land cover classification. If I look at the properties of that data set, I see that this raster data set has 15,000 columns and almost 19,000 rows. Each cell is 30 meters by 30 meters. And so each cell is going to have a single value in it, and that value in this case is going to be an integer. And since it's an integer, you can join attributes to it, and that's how you get these descriptions of the land covers, because each value is associated with a different type of land cover. So lots of raster cells. How do we convert that to a vector? Well, if you zoom in on that land cover and just look at a little piece, we zoomed way in on the land cover, you can see kind of the stair-step nature of the cells. These green cells all have the same value in it. When you convert that to vector, what's going to happen is it's going to convert these adjacent cells that have the same value into a single polygon. So you can see that, in this case, this set of adjacent cells becomes this single polygon. It'll still have the stair-step effect unless you simplify the polygons, which I'll show you in a minute. Okay, our toolbox, this is where you do your converting. You can convert from raster, you can convert to raster. So if I'm going from raster to vector, I can go to points, polylines, polygons. I can do conversions in various ways. So here we have the input raster. I can do the basic conversion and say don't simplify the polygons, keep the stair steps in there. Or I can select an option that lets me simplify, and then what it does is it kind of cuts the corners on the stair steps. So instead of having a stair step thing, you have basically a pointy thing. So that simplifies the polygons, makes it easier to store the information. Otherwise, the vector data set has to store locations for every one of these cell corners, and that makes it pretty storage intensive. When you do the conversion with the raster to polygon tool, you just click simplify. If you want to simplify, you can see that you actually lose some accuracy in your positional data when you do that, but you generalize and you get a storage kick out of it. There's a bunch of rules that you need to follow when you're converting the other way, from vector to raster as opposed to raster to vector. So it depends on what you're converting from, which rules will apply. And so in this case we're looking at points being converted to rasters, and there might be a case where there are multiple points inside of what will become a single raster cell. And so you can set rules, like in this rule here, the rule is going to be the point that occurs, the value that occurs most frequently will be the value that you'll put in the cell. And so here there are 2 greens and 2 blues, so one of those 2 will be the value that the cell gets. There is a lowest ID number, which if there's a tie, the value will be assigned to the lowest ID number. So that's what happens here. This one has the most frequent, but there's another rule you can have, and that's a priority rule, and it's hard to see this, but this has an FID priority, and in this case the blue priority is higher, 2, than the green priority, and so the blue is the value that gets assigned in there. Lines to raster, depending upon the lines and the cell and the raster intersect, you can assign the value to the cell based upon which line segment has the longest length. In this case it would be the blue one. Which line segment or ID number has the maximum combined length. So in this case we have 2 greens, so green is going to be what the value it'll be. And there's another one called maximum length if you use the priority, and so that you can override the length with the priority field. Polygon to raster, here you would have maybe multiple vector polygons that overlap one raster cell. You can say assign the value to whatever polygon is at the center of the cell, whichever polygon occupies the maximum area, and if multiple polygons have the same value, which combined area is the most. So depending upon how you want to do your conversion and how you want the data to go across from vector to raster, you apply these different rules. How do things work when a point falls right on the boundary of a raster? Well, you can see here that the points are assigned to the cell to the inside, to the up to the above and to the left, above and to the right. And so the cells collapse upward and inward. Okay, so let's start with some raster analysis. One of the things you do with rasters a lot is distance measurement. Think of this grid, and this grid has equally spaced cells. You know that makes it a raster. So if I'm going to measure the distance between 2 points on my grid, I can use the Pythagorean theorem to do that a squared plus b squared equals c squared thing and solve for the distance between them along the hypotenuse. And so the distance measurement in rasters, this basic distance measurement is called Euclidean distance, and it's going to use Euclidean geometry, the Pythagorean theorem, to determine what the distance is between those points. You use this distance calculation to do the equivalent of raster buffering. So remember, in vector, a buffer is a polygon that's drawn at a certain distance from a point, a line, or another polygon. Well, in a raster, the calculation calculates the distance from a source cell and stores the value of the distance in the cell. So in this case, the source cell here is right here, and this cell is out here about 30 units from that source. This cell is out about 30 units from this source. So what it does is you give it the source cells, and it's going to calculate the distance from the closest source cell to that source cell. So Euclidean distance gives you a raster of distances. There's also Euclidean direction, which will tell you what direction it is from that cell to the closest source. And then there's Euclidean allocation, which gives you a raster that has the ID number of the source cell that each cell is closest to. So you can imagine in this area right here, it's about the same distance from here to here, but at some point one cell will be closer to this cell and the other cell will be closer to that cell, so the Euclidean allocation will allocate it to this cell and then to that cell. Okay, that was kind of the introduction to some of the things we're going to be doing in raster analysis. Next time I'll get into some more raster analysis, which are things that are kind of similar to what vector overlay is. So how do you do the equivalent of overlays with raster data? And that'll be next time.